Thank you. Okay, so reasoning with LLMs is becoming a very hot topic these days. Obviously, everybody knows about it. It's all over the news. There's a lot of hype around it. And it's really hard to keep up. You know, just last summer, I think we heard about alpha proof system coming out of DeepMind, which a lot of people here might know better about. You know, it won the silver medal at the International Math Olympiad. And just about 4 months ago, I think it was that OpenAI released the O1 model that has really advanced reasoning capabilities. It's really expensive and slow, but you know they're saying that that's really the cost you pay for the reasoning. And then just in the last month, we have all of the DeepSeek craze going on as well. Like they say that, oh, we can do much, you know, similar things to O1, but much more efficiently if we train this like model in this using reinforcement learning and all of that. And then OpenAI is answering back with O3. And we also hear things like, oh, there's some PhD students who are able to train these models for under $50 and they're meeting the performance of O1. So there are lots of different stories going around in the media, and it's really hard to keep up with them. So at the same time, you know, while these models are really getting like really high reasoning capabilities, you know, there are also questions about, are they really doing reasoning? Or are they just doing really advanced pattern matching, and it's just really difficult to tell the difference? So for example, one of this recent work by the study by Apple researchers, they were showing that if you take some of these data sets, these benchmarks, and if you take the question and you just kind of add some irrelevant information to the question, then that causes like this huge degradation in performance of a lot of these language models, including O1 and GPT-4. You can see like there's a big degradation. And so there are these questions floating around, like, are LLMs really doing reasoning? And people are also saying that, you know, they should really be doing formal reasoning so that we are actually sure of, you know, is the reasoning actually logically correct and consistent and so on. Okay. So in this talk, I will kind of, it's really hard to give like a very comprehensive overview of all of the techniques that are going on. There are thousands of papers being published in the area, literally. So I'll be talking about some of the more popular techniques and kind of segmenting it into 4 sections. So starting off with discussing some of the reasoning benchmarks that people use, the more common standard benchmarks that people are using to test these models. And then the prompting approaches, like given an existing LLM, how can you actually prompt it in different ways to get the best kind of reasoning out of it? And then we have training and fine-tuning approaches. How do we take a model? How do we actually optimize it so that it's doing better reasoning? And then finally, I'll touch a little bit upon how we can combine formal reasoning techniques with LLMs. Okay. So starting with benchmarks, so we have like these famous benchmarks like MMLU, Massive Multitask Language Understanding. So this benchmark is a very popular one. It has a lot of breadth, covering different subjects like maths, physics, humanities, economics, and so on. And it's a good mix of like knowledge and reasoning. So you need to have like a lot of knowledge about like different economic theories and so on. But also at the same time, the questions require some degree of reasoning. And they are basically multiple choice questions. And we have other benchmarks like GSMK. This is like more focused on reasoning capabilities. So this benchmark, for example, is focusing on elementary or middle school level mathematics. You're doing simple kind of arithmetic, percentages, basic logical reasoning. And the idea is that can the model actually do step-by-step reasoning? If you have some context, like there's a story about Mrs. Lim, she's getting different, she's milking her cows and getting gallons of milk. If this price per gallon is $3.50, what is the total amount, and so on. And in the data set, we have the question and the reasoning, which is kind of like a mix of natural language and mathematics. And then we have the final answer, which is actually like, well, what is the answer there? So that's a pretty famous benchmark. Getting more advanced is like the math benchmark by Hendricks. This is going into high school, early undergraduate mathematics problems, where you go into algebra, geometry, probability theory, and so on. And as you go into these advanced kind of branches of mathematics, you need more notation. So, sorry. So, you know, this benchmark is using LaTeX notation both in the problems and in the solutions to kind of use some of these advanced notations in mathematics. And then you have the final answer in the boxed annotation down there. So you can use these to actually train the model both on the solution and actually the answer. Right? And going beyond mathematical benchmarks, we also have like pure reasoning kinds of benchmarks, like the law school admissions tests, for example, is a good benchmark. These are real tests for admission to law school where they're testing the analytical ability of students, and they're taking these tests for over a period of 25 years. And and the problems in these kinds of questions are they're not involving a lot of mathematics, but basically there are a lot of constraints. Like a professor, for example, must order look at the 5 students and the order of performances, and there are various constraints, like Kevin must perform earlier than Hakeem, and so on. So that's a pretty good benchmark for testing pure logical reasoning. And then we go on into the more kind of advanced benchmarks like AIM and OmniMath. These are like Olympiad level benchmarks, which are like the most difficult kinds of problems that these students can actually handle. And the Math Vista, for example, is looking at other kinds of mathematical reasoning in visual contexts. So for example, if you have a graph and which portion of the graph is monotonic in range, and so the model needs to do some kind of visual reasoning together with logical reasoning. And if you go to the real extreme, then this is a recent benchmark called Frontier Math. Is like some of the hardest problems in mathematics. Really challenging problems that are come up with by a group of mathematicians from universities around the world. And they're covering really advanced topics like category theory and differential geometry and so on. And these are the kinds of problems that take a few hours up to a few days to solve, even by expert mathematicians. So these are really, for example, really challenging benchmarks. And I think only about 2%, less than 2% of them are actually solved by existing language models like O1. So we see that the frontier math, for example, is totally unsolved, and we see kind of in terms of how much of these benchmarks are actually solved. Sorry. MMLU is pretty much saturated. Math and GSM 8K are also really almost done with the finest models out there. But it's still good to look at these benchmarks, especially math and GSM, when you're thinking about reasoning, especially when you're training smaller models like open source models, and you're trying out some techniques. These are actually kind of the more useful benchmarks to think about, because it's easier for you to understand the solutions as well and to see how well the model is doing. Okay. So going into prompting approaches then. Prompting is all about, basically you're given an existing language model and you want to see how you can prompt it in different ways to get better reasoning out of it. And so chain of thought is obviously like a very popular technique that you use to actually do this kind of reasoning. And the idea is very simple. Basically, you have the question, and instead of asking the model to directly predict the answer, you're asking it to do some kind of, generate tokens to do some kind of reasoning before predicting the answer, right? And this technique is like so inherent now. It's even beyond prompting. Like a lot of these models are already trained to do that, and it's really difficult to actually get them to answer the question directly, even if you try prompting it in that way. So chain of thought is really a popular technique, and it's the basis of like all of these models like O1 and so on. And in their first paper, what they showed was with this kind of reasoning approach, they can reach state-of-the-art performance on this on the Palm model. For example, on GSM 8K, they reached 57%, which was like the best at the time when it came out a few years ago. And what they showed was also that they can do this large-scale kind of basically this kind of chain of thought ability emerges at large scale. So as the models reach these billions of parameters, then it starts emerging. And for smaller models, basically, you don't see a lot of gain if you do this kind of reasoning. And then they tried other kinds of approaches, like equation-only prompting. Like if you only ask it to produce the equations, then it didn't do as well. So the natural language kind of reasoning kind of plays a part in actually getting to the right answer. probably because these models are trained with a lot of data where there is this kind of explanation in natural language. And if you try other things like doing the answer before producing the explanation, then obviously you don't get a lot of gain because the model is kind of like using the reasoning to get closer to the answer. Right? And then going beyond chain of thought, the idea of chain of thought of self-consistency is that basically if you follow a single path of reasoning, then you can, you're likely to make some mistakes and go wrong. But if you explore multiple different paths of reasoning and there's diversity in the paths that you take, and if there's agreement between those different paths of reasoning, then you can actually do much better and get much more confidence in the answers. So you take basically a given problem and you sample multiple paths. You can do temperature sampling or top K or whatever. And then basically you aggregate them using some technique. And what they find is that majority voting kind of works best. And basically show that you get a much stronger boost in performance. So around 3% to 17% in the best case is what they found in their original paper. And again, they showed that as the models get larger, then this kind of thing actually works better. The consistency actually helps with larger models. And around 40 samples, you kind of start plateauing. So you get more gain with the more samples you add, and then around 40 samples is actually like where you start getting diminishing returns. And it outperforms like a bunch of existing methods, like greedy decoding, obviously, with a single path. Or if you rank them by the log probabilities of the results, and you do it that way, then this actually is better because it's more diverse in reasoning. Beam search is also not very diverse. You kind of start with the same path and you start branching out of that, and so you're kind of limited in diversity. And then if you do prompt permutations and all of that, then this method actually outperforms that as well. So that's and I think that Owen models are also doing things like that, producing multiple chains of thought and looking at consistency between them. Okay, and then we go into some of these generalizations, like people have proposed, we can generalize chain of thought in various ways. So for example, we have tree of thought reasoning, where you don't go down a single path, but you kind of branch on alternatives, and you can do backtracking. Like you can use some external verifier, voting mechanisms between like the results at different branches, and backtrack and so on. Graph of thought takes it even further by saying that you can start looping or merging different paths. Like if there's like agreement between different paths, or if there are contradictions, then you can do this kind of parallel reasoning and explore the search space better. And these techniques are obviously heavier techniques because they're involving multiple rounds of LLM calls and multiple ways of prompting it. So they're much more expensive, but they show benefit in certain specialized kinds of problems. And then we have tool integration approaches. So we have a program of thought, for example, which is saying that rather than just doing the reasoning directly with the LLM, we're actually going to produce a program to solve the problem. So for example, on the right here, we see a Python program that's answering this question about what is the 50th number in the sequence. And if you try to do this kind of thing directly, then obviously you're very likely to make mistakes. But if you do symbolic reasoning in this way, then you're kind of like disentangling the computation out of the problem. And so you can just execute this program and get the right answer. So it's a kind of a symbolic reasoning rather than direct concrete reasoning. Right? So the React framework is another example of tool integration approaches where it's kind of like a simple framework saying that, okay, if you're going to incorporate tools, then you want to do it in an interleaf fashion. So you want to think about the problem, and then you have some action that you want to do with the tool. For example, in this case, if you have a question that involves doing some searches using a search API, then you can first have a thought and then do a certain search. Then you have an observation about what is the answer, and then you have another thought, and then you can kind of interleave things in this way to arrive at the right answer. So that's a more kind of a generic kind of a prompting framework that you can use. Okay. And then there are a bunch of different kinds of problem reformulation approaches. So this is the idea that you take the original problem and then you solve different kinds of problems that you generate in order to help solve the original problem. So compositional prompting is an obvious way to do this. Like you have a complex problem, and can you first have a prompt that decomposes it into smaller problems, and then you solve the smaller problems, you add them to the prompt, and then you try to solve the more complex problem. And so this is shown improvement in various tasks, but also the decomposition strategy is not clear in all possible domains, and so you need to think a little bit about whether it's applicable in certain domains or not. So another example that's interesting is this reasoning by analogy, where you take a problem and you generate lots of different kinds of analogous problems that you can solve. For example, if you have you want to find the area of a square with these vertices, you might come up with a kind of a related question, which is, what is the area of the square with a side of length 5? You solve that first, and then you kind of like take that to lead the reasoning down the model, to do the right reasoning down the right path. And again, it's similar kinds of limitations, like what if your analogies are poor, or what if you incorrectly solve the analogous problems, and you might propagate the errors, and so those kinds of issues also arise. Okay, and finally, backwards verification. That's another interesting example where you're trying to get more confidence in the answer from the language models. So the idea is that basically you can solve the initial problem, and then once you get the answer to the problem, then you can mask some of the input parameters to the original problem, and then try to predict that, assuming that this is the answer. So for example, if the answer is 2 in this case, then you can get back one of the original parameters, which is 10. Then you kind of have like this consistency between forward and backward reasoning, right? That these are the complementary problems that I can try to solve, and if the answer is consistent, then I have a very high degree of confidence. So those are some of the interesting techniques that people have been using to do prompting in various ways. So getting to training and fine-tuning approaches, sorry about the problem there. So these are techniques that are trying to train the model to be better at reasoning, right? So one example is this Torah project, where they were trying to use GPT-4 as a teacher model to train a better model at using these tools. So for example, we have, if you just try to do pure rationale-based reasoning, or if you try to do pure program-based reasoning, then you're likely to hit errors. And the idea is that you have a trajectory of looking at the results similar to React, and then you have this interleaving of looking at the observations and then getting to the right answer. So what they did was that they used GPT-4 as a teacher model to train on large amounts of data. And they showed that with a 34 billion parameter model, they can get greater than 50% accuracy on the MAT data set, and also beating GPT-4 with just pure chain of thought. And the way that they did this basically was like there were 2 phases. So you have the imitation learning phase, where they generate a large number of trajectories, about 16,000 trajectories using GPT-4, where the trajectories are these rationale, action, and output kind of sequences. They run the model, and then they fine-tune on these trajectories to actually get the initial checkpoint where they get the initial model. And then in the second phase, they kind of expand on this in terms of the diversity. So looking at trying to sample many different paths from the trained model, like 64 different trajectories, and then filtering out the ones that are actually correct, and then even correcting some of those using this a smaller teacher model. And in this way, they ended up with like a lot of examples for a given problem, and over 200K trajectories. When they do the final model training, then they can show that they achieve much better performance in this way. So that was an interesting idea, how to use like a teacher model to do better training. So wizard math is another example of using a teacher model and using reinforcement learning. So in this case, they start off by doing this data augmentation using this evolve instruct paradigm, where they take GPT-4 on starting from a seed set like GSM or math, and they try to create more challenging or less challenging problems. Like you might create harder problems by adding more constraints, or easier problems by removing some of the constraints and so on. And that's just to get more generalization in terms of the data. And so that was a way to get like more data. And then also getting the ground truth of that from GPT-4 and fine-tuning a base model like Llama on that, right? And then in the final step, they do is this reinforcement learning, where they have reward models both for the quality of the instruction and the quality of the process, the result, right? So the instruction quality is looking at like the difficulty, the clarity of the question, and the process reward is looking at each of the steps in the reasoning. And both of these reward models are trained with data from GPT-4 to label like how good the results are and how good the instructions are. And so with these kind of reward models, when they do reinforcement learning, they show that you can achieve like really high performance even on small open source models. So their key results are showing that their best model at 70 billion parameters, significantly beats a lot of the open source models, the proprietary models. And even with the 7 billion parameter model, they can do better than GPT-4 on the math data set. And even down to actually 1.5 billion, they can do really good on both GSM and math data sets, which was pretty impressive. Okay. So touching a little bit on DeepSeek, and they're famous for a lot of different things, a lot of different techniques that they're using. But one of the interesting things that they showed in their recent paper was that you can go really far with just reinforcement learning alone. So their R10 model, for example, they trained with RL only without any supervised fine-tuning. And in terms of like the technique, the reward was not based on a reward model, but more rule-based. And one of the different things that they were using was this group relative policy optimization. So the idea is you get rid of the critic model, so you don't have to like have a separate model that kind of is estimating the value on any given input. But you use the original model itself to sample many possible answers, and then you take the average of the group and you kind of get the advantage that way, like anything performing better than the average gets higher reward and so on. So that's more of an optimization. I don't know how much that affects the actual, the final accuracy of the model. But basically, if they start this on a base model like their V3 model, then they show that they can go from 15% up to about 70, 80% on the AIM benchmarks. So that's reaching kind of like O1 level accuracy on this really difficult mathematical benchmark. And interestingly, they found that the model is also kind of learning these kinds of behaviors like reflection and self-verification. So they had this aha moment where the model was saying that, oh, wait, maybe I've made a mistake, or let's rethink and try to follow a different kind of reasoning path in the middle of the proof. One of the other things that they found was that long chains of thoughts were automatically being generated by these models, by the model as it was learning. So as we had more training iterations, you see that the length of the chain of thoughts was actually increasing. So this was kind of like an emergent behavior that the model wasn't actually trained to do from scratch. So those were some interesting findings in that paper. But this base model had issues around readability, like the proofs were not actually very readable, and also they were mixing different languages and so on. So what they actually did was in their REST model, which is the R1 model, is actually a mix of reinforcement learning and fine-tuning. So they have 4 stages here. Initially, they start with some cold start data. So they have long chains of thought that they obtain from various kinds of techniques like prompting or getting it from human annotations. And with that initial data, they do some fine-tuning first. And then they go on into the RL step as before. And here they throw in some more rewards for consistency of the language and so on. And so they get to a checkpoint where they're pretty good at reasoning, and then they start fine-tuning by including a lot of other kinds of non-reasoning data and fine-tuning based on that. And then in the final RL stage, they kind of mix these two reward signals. The reasoning rewards are more rule-based, and the non-reasoning rewards are actually based on reward models. So with this kind of like a 4-stage pipeline, they get to a really high performance, which, as you know, the R1 model is very comparable to O1 on a lot of these difficult maths benchmarks. Okay. So finally, sorry, any questions, please feel free to ask. So finally, I'll touch on this area a little bit on LLMs and formal reasoning. So basically, the idea is that we have all of these automated reasoning tools like symbolic solvers, satisfiability solvers, and theorem provers, and they can actually guarantee soundness of the reasoning. But they also require that the problem has to be specified in the formal language in the first place in order for them to be, to actually solve it correctly. So this, for example, here is an example from the law school examinations data set, where you have, like a bunch of students, and they need to visit some cities, and then there's conditions around various constraints, like Sharon visits a different city than Paul, and so on. And down here you can see a specification of this problem in the formal Z3 satisfiability solver. And in this formalization you can see that you declare types for students, cities, and then you might have some uninterpreted functions like visits. So if a student visits a city, and then you can formalize each of the constraints from the natural language, like saying visits Sharon not equal to visits Paul. Or you can use quantification, like for all students S1, there exists a student S2, such that S1 is not equal to S2, and so on, right? So those are like the formalizations of these constraints in this formal logical language. And so what some of these recent works have done is to take the language model to create this formal specification and then use the solver to just get the answer, right? And they show that that works better than just a normal chain of thought and so on. But the key issue here is that you need to get to the right formalization of the problem. So, so for example, in this case, if you get any of this wrong, like you use the wrong quantifier or anything, then you're basically solving the wrong problem, right? So this is where we've been doing some work recently in terms of addressing this formalization issue. And one of the things that we've tried is that can we use both a mix of abstract and concrete inference to get stronger, more robust formalizations of the problems, right? So let's say we have the natural language problem description, and we run the language model, and we get a formal description. What we also do in addition to that is that the language model generates concrete instantiations of the problem. So we take each of the constraints in the input problem, and we say, like, what are some concrete instantiations? And then we also formalize them into the same language. And then we can use the solver itself to check the consistency between the concrete instantiations and the abstract formalization. So to show you an example of this, basically let's say that we have a simple constraint like Paul and Laurie cannot visit any of the same cities. And down here we have an abstract formalization that says, oh, there exists a C such that it's not the case that visit Paul C and Laurie visit Laurie C, right? At the same time, we get the language model to produce some concrete instances purely from the natural language. So what are some concrete instantiations? So Paul visits Montreal and Laurie visits Toronto is a satisfying example. A negative example might be Paul and Laurie cannot both visit Ottawa, right? And then it's also translating that into the concrete formalization. We run the solver to say that, okay, if I give you the abstract constraint and one of these concrete constraints, is it satisfiable? And so it satisfies that one. But in the second case, we find that the solver verification fails, right? And the reason that it's failing is because the quantification actually down here is wrong. So you shouldn't be using the exist quantifier, you should be using the for all quantifier, because you should be saying that for all cities C, it's not possible for them to visit the same city. So this is how the concrete instantiations can help us to detect when the formalization is going wrong. And both, so in this case, if you correct, for example, if you had the right formalization, you were using the for all quantifier, then of course both of these examples would be satisfied, right? So in this way, we kind of get more confidence. I mean, obviously both things can go wrong. The abstract translation can be wrong, and the LLM could also make mistakes in the concrete instantiations. But it's basically the agreement between the two that actually gives you a very high degree of confidence. Like whenever there is agreement, then you get almost near perfect certainty in practice, actually, as we found in our experiments. But what do you do with that? Like, you have a very powerful signal of verification that's telling you, in some cases, I can find that your formalization is really correct. But what you can do is that once you have that kind of verification signal, then you can use it to do refinement on the original formalization, right? So if you have a failing instantiation, for example, you can send it back to the language model, and you can say, can you reason further about this? And is the problem in the formalization? Can you update that? Or is it in the instantiation itself? And also at the same time, you can say that, oh, I have this strong signal of verification, so I can do temperature sampling and create many possible candidate formalizations and then choose the ones that actually satisfy this kind of verification. And so when we did this, for example, taking this the law school examinations data set, what we see with plain GPT-4, we're down there around 30% on this benchmark. Chain of thought does only slightly better. If you combine the language models with solvers directly, as in prior work, then you go up to around 43%. And the average human performance here is around 59%. But if you do this kind of instantiation-based verification, then we go up to around 71% on this data set in just pure answer accuracy. But what's more interesting is that in the cases that we're able to verify, we go up to around 100% accuracy, actually literally 100% with GPT-4, even though like the coverage of cases is around 21%. So on a small proportion of cases, the model is really confident of the answer. So it can actually come back not just with the answer, but an additional signal saying that, yes, I verified this result, and I can actually have a very high degree of confidence here. And what we found was that as the models get weaker, like if you go to GPT 3.5, the precision still remains very high. It's around 97% of the precision of verification, but the coverage might fall. So that's like one of the things about this technique is that it kind of it prefers precision, and the precision is more robust, and while the coverage might actually go down. So yeah, so that's some of the work on formalization. And then finally, it would be, of course, good to mention the shining example of alpha proof, which has come out of DeepMind, where the focus is really like, the formalization is one step of the process to actually go from the natural language to the formal statements. But then the proof search is really like where you want to search this really huge space of possible formal proofs of a problem, right? So in this case, they use the lean theorem prover, which is this really useful tool that mathematicians use when they want to formalize a problem. They can express it in this formal language, and then it's a proof assistant. Basically, you can write out a proof, and then it tells you if there are any errors in the proof or if it's valid. And so in this case, what they do is that they use reinforcement learning to do the search in the space of all possible lean programs. And so they train on an initial model, and then they use this Monte Carlo tree search to kind of get the neural model to, at every step, it kind of proposes, like, looks at the most probable proof steps, and then it goes down the tree and then does back propagation to update the neural model as well. And this is based on the AlphaZero approach, which they also used for other domains like AlphaGo and chess and so on. And one of the other interesting things is that they also use the model also self-generates variations of the original problem. So if you have so it's actually learning in real time. So given a new problem, it will explore different variations and also learn and converge towards the correct solution. And as we know, with this technique, they're able to solve like some of the most difficult problems in the Maths Olympiad. Okay. So yeah, so that was just to give you like a very high level kind of flavor of the different kinds of techniques that you can use. And what we know is that these language models have really achieved really amazing kind of capabilities in reasoning, but they still make unpredictable errors. And as these tasks get really complicated, then it's really difficult to spot those errors. So what is really kind of missing right now is this deeper integration of formal reasoning in these models. And there are approaches that are trying to bring these techniques deeper into the model, like into the loss function or into the architecture of these models, but they've only shown kind of like progress in specialized domains. So we're not really seeing a lot of a general impact of these techniques yet. The other related kind of aspect is that we need verification and confidence in addition to this kind of just pure accuracy on benchmarks. And so reliability in the real world actually needs this kind of verification. So finally, it's, people are talking about is AGI here? It's kind of here because these models are really good at general reasoning, but we need to kind of combine formality and bring it at formality at scale in order to really go towards the superhuman kind of reasoning that we're aiming for. So yeah, that's it. Thank you. Any questions? Yeah.
So I have a question. When the models currently we are using, when they spread to the benchmarks currently we have it, are we? So the models currently performing very well with these benchmarks. So once they suppress those benchmarks, do you think will there be another benchmarks in order to test them? Because how we can understand if the models that created are smarter than us and does not deceive us? I mean, there's a philosophical way to that question as well. Yeah. But how can we measure their performance once they suppress a benchmark?
Yes. So obviously they're coming up with more and more difficult benchmarks. So for example, frontier math is an effort in that direction, right? And you can do things like withholding the ground truth from the models and so on, that this is like hidden and we can evaluate that. But eventually it leaks and it gets out one way or the other, right? So that is a problem, and as the models get better, like you say, they come up with more difficult benchmarks. But one of the other ways to solve that is to have kind of like the formal systems that we have, right? Like for example, if you have something like lean, where you have a very long sequence of steps, you can automatically know that this is a valid proof or not, right? And if your system is kind of like coming up with some answer to the question, if you can formalize that, then we can have 100% verification in the correctness.
Okay.
Right? So
One other question about the automated reasoning tools. I haven't heard of them until this topic and today. What are the best automated reasoning tools currently?
Yeah, so Lean is good, but it's not fully automatic. So it's a proof assistant, and that's used for like really advanced mathematics. Z3, Isabelle are other examples of theorem provers, and Z3 is much more automated, so it can do fully automatic reasoning. There's the Coq proof assistant as well. So those are some of the example tools.
Okay, thank you.
Sir?
Yes.
Sir, I want to ask, like, what is your opinion on the ARC AGI benchmark?
Oh, yeah.
And what do you think OpenAI O3 model used to solve that and achieve like 70 to 80% accuracy on that?
Yeah, so ARC is interesting, but it doesn't, it doesn't feel like AGI, because it seems like actually pretty much like something out of the 90s. It's like, it's a very specialized domain. And also I feel like it's kind of, like humans find it easy because it's a lot of visual reasoning, right? Whereas, when you give it to a model like O3, you translate that, and the representation is more mathematical in the sense. And so there is a question of whether it's obviously, if you give that representation to a human, there's no chance of them solving it, right? So it's the question about the representations as well. So it's an interesting benchmark, and it's great that they're doing really well on it. But I don't think that it kind of captures general reasoning that well. You know, like some of these other benchmarks are much more fascinating, I think, than ARC. So it's more of a thing. I don't know exactly how O3 is doing it. They have I don't know. They haven't revealed much about how they're actually addressing it, though.
Okay, thank you.
Yes.
Thank you for the talk. So this might be a bit naive, but it seems to me that so we're doing two things at the same time with these reasoning approaches. So we're doing reasoning like in a chain of thought, and at the same time we're scaling the inference time, right? So my question is, do we know if there are there techniques just to scale the inference time without having to do something like reasoning? Because I'm curious to know if the improvement comes purely from just scaling compute, even if it doesn't have to do anything with reasoning. Like, for example, in vision, if I were just to do things similarly in vision, I could scale the inference time by increasing the resolution of the images, and that almost always improves performance. Yeah, even though I'm not really reasoning about the image, I'm just like scaling the inference time.
Yes.
So I don't know if there is something similar in language.
Yeah. So is the question like, if you do direct reasoning, what is the reason that the chain of thought performs better?
Yeah, and what I'm saying, yeah, because I'm wondering if it's just maybe a proxy or another way for just scaling the inference compute, but it doesn't have to do with reasoning itself, like. I don't know. I mean, I'm just speculating.
Yes. It's a good point. I mean, because you're doing much more compute, you're generating many more tokens, and so you're getting it. But maybe you can think of it as a way that how do we use the additional compute effectively, right? So you're doing multiple token generations, but are you generating the right tokens? And so that's where the guidance from chain of thought really comes in, right? So, yeah. Yes. Yeah. So one of the other interesting areas that we're looking at, some of the people at QCRI are looking at interpretability of these language models, right? So looking at what is actually the neurons that are actually firing when you do a certain task. So one of the questions that we're currently thinking about is, if you have the same task and you do a chain of thought versus a direct answer, what are the common neurons that are being fired in the two cases, right? And so can we actually detect which parts of the network are being activated? And so will that give us some insight as to whether the model does the same kind of mathematical reasoning with a direct prompt as it would with a chain of thought prompt? But there is obvious benefit to it, and it's hard to put the finger on where exactly it's coming from. Yeah.
Hi, Mohammed. Here.
Sorry. Oh, okay. Hi.
Thank you for the informative talk. I have a few doubts, and please bear with me. These are threefold or twofold. First, are LLMs stochastic or probabilistic or deterministic? I've done some reading, but the more I read, the more confused I become for some reason. So if you could answer this first.
I would say that they're definitely probabilistic, right? They're inherently based on probabilities, and it's a very high degree of probabilistic reasoning that is, if you get it to a certain degree, you almost like get a higher degree of determinism, right, when you're solving this problem. So it's based on next token generation, and they're generating the most likely outcome, right? So I'm not sure why you're thinking that are they probabilistic or deterministic? What makes you think that they're deterministic in that sense?
Based on the prompts that we provide to it, they become more and more gullible. Like when you try to lead it into an incorrect direction, they are led to that direction. So I was wondering, how can we use formal verification or formal methods to make it realize that the response it is producing, it's actually correct, and not give so much weightage to the prompt itself. So That's where the confusion lies.
I see. So how can we use formal methods to make it not obey the prompt? But
Or not to give it so much importance that the way we want to lead it, it's led that way. So if I want it to agree with me, it eventually will agree with me.
Yes.
So is there any room for research over there, or are there any directions, or what are your thoughts on that?
Yeah. I mean, definitely, it depends on the goal, right? So sometimes, if maybe you do want it to agree with you, even if you're wrong, right? so in that sense, they're general, right? And so the prompting framework is basically there. But if you want to enforce these formal rules, then definitely incorporating some kind of formal logical techniques could help. The main problem with these techniques is everything has to be formalized, right? For example, there's a lot of, in normal reasoning, natural language reasoning, there are a lot of hidden assumptions. Not everything is a complete logical deduction, right? Because it's using some inherent missing information. And so if you want to use these formal methods, you have to spell it out literally step by step. A implies B, B implies C. And getting that done is actually really the challenge here, right? So if you want to do it at that scale, that's something that's missing right now, and we need to work on that, right? But I think it's definitely possible. Like if you enforce some kind of logical constraints on the prompt, then definitely the LLM should be able to determine that, I think, with these techniques.
Yes, as a background, as a tenant, I had a dispute with my landlord, and I was arguing with the LLM. So first I pretended to be the tenant, and it was proving me correct. And then I pretended to be the landlord, and the landlord was also correct.
Yeah, and you would notice that it also happens after maybe 2 or 3 rounds of interaction.
Exactly.
That it kind of gives up, and then it just starts agreeing with you, and it starts making less sense.
Exactly.
And if you do it on the initial round, then it provides a very kind of like independent, thought out answer, right? Yeah. So yeah, it depends a lot on the way that these models are trained, definitely.
Thank you. Thank you.
Yes.
Hi. First of all, thank you for this good overview. And my question is on, I was working on the distillation techniques and working on the Google's new paper, reverse thinking for the reasoning data. And I saw that like Google using creating the synthetic data sets for the reasoning tasks and training the smaller models on them, and they get a higher performance, and the paper is about a special technique. And then I saw the DeepSeek paper, and then they also state that they when they try to train the small models, rather than using the RL techniques, they saw that the distilled synthetic data from the bigger model gets much better performance for cheaper training costs. So maybe as we don't have the big models, how can we more efficiently train our small models for these reasoning tasks? Maybe formal reasoning can help. What are your comments on this?
So are you talking about cases where you don't have access to the big models?
Yeah.
Which is becoming less common now, right? Especially with some of these models coming up. But yeah,
no,
definitely.
I mean, we cannot get the data, generated data from them, maybe.
Yes, that's right. So I think it's definitely possible, and depends on the kinds of problems that you're talking about. With an automated theorem prover like Z3, you have first order logic, and you can do basic logical kind of reasoning tasks, and it can do those pretty well automatically, right? As you start going into more advanced kind of territory like mathematical notations, and you need more mathematical knowledge, then you can use a theorem prover like Lean, but you need a lot of hard coding of like the specific mathematical theories that you're thinking about, right? So a lot of domain knowledge needs to be there in these tools. But if you have that, then definitely you can use those systems to kind of generate the ground truth, like you're saying. So you can imagine a model that's producing like huge thousands of problems, and some of them might not make sense, and whereas others might, and then you can just verify them with the theorem prover. So that's definitely a great idea. You can definitely try things like that, I think. But it's difficult to scale these formal methods up. I think that's really the problem. Yeah.
Thank you.
I want to like what Professor Ibrahim asked about whether scaling is really important for the models. So I did a test where I used the thinking tokens of DeepSeek R1, and I'm running Llama 370B locally. So I just copied the thinking tokens, and it like drastically improved the performance of the 70B model, sorry, not 7B model, which you can run locally. So I think the chain of thought is really important, and particularly the RL part is really important. I don't think so that scaling is of course important, but we can easily improve the performance of the smaller models just by using RL or like properly using chain of thought.
Yes, yes. I think they showed that in their first paper as well, that RL was kind of like capturing, at that point, you know, they weren't making a big deal out of RL, but it was capturing what you would what's already inherently available in the model. So the kind of inference time scale up is usually like doing multiple sampling and consistency and all of that. And that kind of thing, the RL is able to capture out, I think. So yeah, so that might be possible, definitely, yeah.
Sorry.
No.
Very back. I just have one question on the scalability of things. So obviously the modality of language takes you a really long time to convey a concept. Like what I'm doing right now, I have to give a context about what I'm doing, and then I need to ask you the question. Obviously, education sciences and neuroscience looked into this. How do we learn things as a human? We never reason from ground zero, right? We create concept, and then we start reasoning from the concept. We say, okay, giving the sunrise from the east, I think. Given the sunrise from the east, you start from that. You don't describe the movement of Earth. You don't describe the sun movement. You don't describe all of this. You start from one concept and move on. But it seems today we reason with LLMs on a token level. So even if you go use any of the reasoning models, you see they generate millions of tokens just so they can answer one of specific questions. And if you follow their reasoning, well, token reasoning, is just them trying to reach one of those base concepts. Exactly what I have just done. I spent 2 minutes just to describe the concept I'm trying to get to. I'm wondering, I'm not very familiar with the theorem proving literature. Is there any work on like trying to verify specific concepts and then train models on a concept level basis as a token? Like you make the concept itself as a token and use that to distil information. I'm also on the camp of scaling is all you need. Obviously, if you have infinite memory, infinite flops, you can recall the information from the beginning of Earth and verify it till today. So I think scaling, it will get you there, but do we need to burn so many trees to get there? So that's maybe a tangent to the two questions asked before. So yeah, maybe the question I have is, do we have verifiable concept-driven token in the literature? Are you aware of anything or something like that? Thanks.
Yeah. So are you saying that you want to explicitly extract these conceptual reasoning strategies maybe, and then kind of use that to hard code them in some way in the model so that it performs better?
Exactly. Those are we have managed to verify, so we have spent all the compute already to verify them, and then these become the token of your model.
Yes. So extracting these out of the model. So there are various works that try to, enforce them in the model. Extracting them out and seeing about that. There must be some work in the interpretability kind of literature, but nothing is specifically coming to mind. But essentially, that's basically what the models are doing, hopefully automatically, right? When they're being trained on these large-scale like mathematical proofs, then they're kind of learning these strategies. And so what you're saying is that can we kind of like make them more explicit?
Exactly.
There must be definitely
spending the flops to do that.
Yeah, exactly. And I suppose model distillation could be thought of as another way of doing that.
That's a good point.
Yeah, like you train the huge model that's already learned those strategies, and then you try to kind of compress it down. Yeah, there must be some work in that area, but nothing is really coming to mind. That's an interesting idea.
Thank you.
Anything else? Okay. Great. Thank you.